Hi, welcome back to my channel and welcome again here in my home province. So for today, we will be talking about the well-ordering principle and the principle of mathematical induction. So for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. And for those who have been here for a very long time, thank you so much for your undying support. Okay, so let's start now. So let's start first with the well-ordering principle. So when we say well-ordering principle, it actually says that the positive integers are well-ordered, meaning to say that by the definition, every non-empty subset M of the set of natural numbers has a least element. So say for example, if you have let's say the sets 5, 8, 7, 4, 6. So technically this is a subset of n, and so this set has a least element. So in this case, the least element is 4. Okay, so this principle actually is a very strong principle in the sense that this could be a counterpart of our principle of mathematical induction. In fact, this principle about well-ordering of positive integers is actually used for some statements that has something to do with positive integers. So we can use that to prove those given statements. So okay, so let's consider an example wherein we can use the well-ordering principle for us to show the claim here. So the claim here is there are no positive integers strictly between 0 and 1. So the thought here is that if you have 0 and 1 here, so you cannot find any positive integers in between these two numbers. That's it. Okay, to prove on this using the well-ordering principle, well, let S be the set of integers x. So be the set x, okay, such that your x is in between 0 and 1, okay? So that will be your assumption. So you're actually showing this by a contradiction. Okay, so suppose S be non-empty. So suppose S is non-empty. And let N be the smallest element So in this part of the statement here, this is where the the entrance of our well-ordering principle. So we assume the smallest element according to the well-ordering principle in the sense that we assume that S is non-empty. Okay, so now that we assume N to be the smallest element, then that is your N is less than 1. Technically because, of course, your set S here is actually coming from this strict interval, and that all the numbers inside are actually less than 1. Okay? So you have N minus 1. So, but multiplying both sides by N, we have what happened to this? This becomes N squared is less than 1. Okay. Okay, so remember that the square of the positive integer is actually a positive integer. So n squared, so since this is a positive integer, this n squared, I'm sorry, this should be n here. So we now have this, okay? So meaning to say that the n squared is also a member of our set S here. This is now a contradiction. Why? We assume that n here is the smallest integer. I mean, the smallest element of the set. But in turns out that there is an n squared to be the smallest of n. Okay? Hence, S is empty. And so S is empty. This proves the claim that there are no positive integers strictly between 0 and 1. And we have now shown the proof. That's it. Okay, so we have another claim here, and it says that every positive integer greater than 1 has a prime divisor. So we will show these using the concept of the well-ordering principle. So to prove that, let's assume by contradiction again. So let S be the set of positive integers greater than 1 with no prime divisor. Okay. So suppose S is non-empty here. So if S is non-empty, so we can now use the well-ordering principle. So we can assign a least element. So in this case, let n be the smallest element Okay, now in this case, n here, so note that n should not be prime. Be prime since n divides itself. Okay, so n should not be prime since the n divide itself. So otherwise, n, what happened if it's not, if it were a prime? So n be its own prime divisor, and so we're done with this. So I'm gonna underline this, the reason why we note that n should not be prime, since if it were a prime then we're done. So okay, now so in this case, since n is not a prime, so n is obviously a composite number. Okay, so it must have been a divisor of d. So if we have a number in between d and n here, it's technically have to be an inequality between those numbers. Okay, so n is composite. Okay, and it must have a divisor. Okay, so for instance, we call this a divisor, say d. Okay, with what is d? So of course our d here is in between 1 and n. Technically, because of course the set of all numbers that having no prime divisor are actually greater than 1, as we assumed earlier. So since n here is the smallest integer here, or the smallest element of the set S, so our d here have a prime divisor in this case. So it has a prime divisor. So d here a prime divisor. Oh yeah, so d has a prime divisor, because if we may assume that d has no prime divisor, then we are actually showing the contradiction here. So if d has a prime divisor, let's say p, then this implies p divides d. Okay, but remember, our d here divides n, implying p also divides n. So this is already a contradiction that to the fact that we assume that our elements are numbers greater than 1 has no prime divisor. So this is a contradiction, therefore S is empty. Okay, which means to say that our statement here is false. Therefore, every positive integer greater than 1 has a prime divisor. That's it. Okay, so we're now on our principle of mathematical induction. So the principle of mathematical induction is actually one of the powerful tool in proving claims in math, like theorems, lemmas, corollary, and such, in such a way that the statements that we are going to prove or the claim that we are going to prove is that does actually involve with positive integers. So in this case, we're actually dealing with the will ordering principle as well. Okay, according to the principle of mathematical induction, it says here that let P of n be the statement for all n great n. Okay, so according to the principle of mathematical induction, it says here that let P of n be the statements for all n in the set of natural numbers, and suppose P of n sub 0 is true for some integer in n sub 0. Okay, in this case. So if for all integers k with k greater than, so as you might see k greater than or equal to n sub 0, your p of k implies p of k plus 1 is true. Then, so this is actually here, then p of n is true for all integers greater than n sub 0. So to see directly on that, we will consider an example. So our example here is prove that n factorial greater than 2 to the n. I mean, prove that n factorial is greater than 2 to the n for all n greater than or equal to 4. Okay, so this means to say that our statement here is n greater factorial is greater than 2 to the n for every n greater than or equal to 4. So meaning to say that our set here is the set of all positive integers having the least element 4, because we have already the condition that n should be greater than or equal to 4. So to say on that, so to show on that proof, okay, so suppose our P of n here is the statement n factorial greater than 2 to the n for all n greater than or equal to 4. So we will check for the least element. The least element here is 4. So we will check. Our n here is 4, so we have 4 factorial. So note that 4 factorial, as you can see, 4 factorial is 24. And this is greater than 16. And our 16 here is 2 to the 4. Okay. So P of 4 is true. Okay, so what does the principle of mathematical induction says again? You have to assume P of k, and then you have to get the result when whether it's P of k plus 1 is true. So suppose P of k is true for all k greater than or equal to 4. Then, what is P of k plus 1? So let's say P of k plus 1. So that's technically k plus 1 factorial. So we have k plus 1 factorial. Okay. Now, remember that k plus 1 factorial, I can write that as k plus 1, and that's k factorial. And as you know, k factorial is already greater than 2 to the k. So therefore, this is greater than k plus 1 times 2 to the k. Okay. And 2 to the k, I mean, k plus 1 is greater than k, it's k alone. And then in this case, I would say this is greater than 2 to the k times 2. Because remember, your k is greater than or equal to 4. So k plus 1 is greater than or equal to 5, and so it's greater than or equal to 2. And so therefore, this is your 2 to the k times 2, that's equal to 2 to the k plus 1. So this is actually the statement for p of k plus 1. Thus, p of k plus 1 is true. Therefore, this implies that p of n is true. It's true. And so we have proven the claim. That's it. Okay, so let's consider another example here. So we have to show that the summation of 1 over I times I plus 1, I from 1 to n, is actually n over n plus 1. So to prove on that, okay, again, let assume that p of n is the statement here. So let p of n be the statement 1 over I times I plus 1, I from 1 to n equals n over n plus 1. So in this case, the least element starts at 1. I mean, the index starts at 1, so the least element is 1. Okay. So for I equals 1, what happened? If I equals 1, then the sum of 1 over I plus 1, I from 1, and it ends with 1 here. It sounds so awkward to write that way. But for the purpose that it is very clear to us, so I'm gonna write the summation here with index starting from 1 and ends in 1. Okay, so this becomes 1 over 1 times 1 plus 1, and this is 1 half. And similarly, since we assume that our I here is 1, so it ends in 1, technically our n here is 1. So this is technically, if I'm gonna show this is 1 over 1 plus 1, and that's equal to 1 half. Okay, so p of 1 is true. Okay, now let us consider, suppose p of k is true. So if p of k is true, then I would have I from 1 to k of 1, I'm sorry, I plus 1, and this is equal to k over k plus 1. Okay. Now, let's examine about a p of k plus 1. So, let's say this is I from 1 to k of 1 over, this is k plus 1 this time. So this is k, I'm sorry, this is I plus 1. So basically, I would have 1, okay, I'm gonna break them down. This becomes summation of 1 over I plus 1, and in this case it's 1 to k, but there's additional. This is equal to 1 over k plus 1, and that is k plus 2. Meaning to say that I substitute k plus 1 to the value of I here. Okay. Now remember, this one here, this is already equal to here. So this is equal to this above k plus 1. So therefore, I can have k over k plus 1, and then I would add that with 1 over k plus 1 and k plus 2. Okay, get it? So this is elementary operation of algebra. So I have denominator here, the LCD of the denominator here is k plus 1, k plus 2. So if I divide this by the first denominator, I would get k plus 2 times k. So that's k plus 2 here, and that is plus 1. Okay. And if I'm gonna simplify this, I would end up having k squared plus 2k plus 1. And so the denominator here, I would have k plus 1 over k plus 2. Okay. Now, note that k plus 1, k squared plus 2k plus 1, this is equivalent to k plus 1 quantity squared over k plus 1, k plus 2. So this will be cancelled, so you're left with k plus 1 over k plus 2. And so if you take a look into this is already the k plus 1, k plus 2 statement for p of k plus 1. Therefore, p of k plus 1 is true. Hence, proven. That's it. Okay, so let's consider another example again. So for all integers, let's show that this I here, summation of I from 1 to n, this is the same as n times n plus 1 over 2. So meaning to say, in this case, our least element here is 1 because the index starts at 1. So, to show the proof on that, let P of n, let's say P of m rather, be the statement, this one. That's I from 1 to n, and that's equal to n times n plus 1 over 2. Okay, then what happened to our P of 1? So let's say, I'm sorry, why it's m? It should be n here. So what our P of 1, so that means 1 here, that's actually 1 times 1 plus 1, and that's 2. So technically, they're equal. So P of 1 is true. So it's n here, sorry. Now, suppose P of k is true, then we have the summation of I from 1 to k, and that's equivalent to k of k plus 1 over 2. Okay, let's examine the p of k plus 1 here. So summation of I from 1 to k plus 1, that is, I can write that as summation of I from 1 to k plus 1, and I have additional of k plus 1 here. Okay, and observe that we all know that this is already as an equivalent to that. So meaning to say that I can write this as k of k plus 1 over 2 plus k plus 1. So I have 2k of k plus 1, and I get 2k plus 2. Okay, then I would get k squared plus k plus 2k plus 2 all over 2, and so I get k squared plus 3k plus 2 over 2, and I can factor this out into k plus 2 and k plus 1 all over 2. So technically this is the same as I can swap this is k plus 1 and this is k plus 2. So technically this is already the p of k plus 1. Okay, so therefore the p of k plus 1 is true, and so everything else follows, and therefore the claim has been proven. So I'm not gonna write it down here, but I hope you get the gist of it. So if you have any questions or clarification, you can comment down there so that I would know and we can be able to discuss on that. If you think you need a lot of examples for these well-ordering principle and principle of mathematical induction, you can comment down there. For now, I'm gonna stop it for now, and that's all for now. So if you have a petition, shall I say, if you comment down there to provide for me to provide a lot of examples, I would do that for you. And if you have any topics that you'd like me to discuss here, then comment down there as well. Or you can go to my page on Facebook so that I would be able to address you well. Okay, so thank you so much, and that's all for now. Thank you so much for watching. Have a great day to you. And by the way, don't forget to click if you haven't subscribed yet. Bye for now.